Okay, go ahead.
All right. Hi, everyone. This is Dippy here. So this is a continuation of our session from the last week, where we talked about like basics of recursion and as well as tail recursion. Today, I'll be talking about backtracking and how we use recursion there. And yeah, we'll particularly look at two problems, and queens and Sudoku solver. So let me share my screen and can you all see my screen here with this tech?
Yeah.
Okay. All right, so let's get started. So before jumping into the problem specifically, let's talk about a conceptual big idea about it, right? Given a problem, how do you identify when backtracking is a potential approach to go? Uh, so would anyone like to share their thoughts on how you approach this concept? I mean, any ideas you have like about this topic?
Can I tell? Hello?
Hello?
Yeah,
Yeah.
yeah. So I guess if you talk about backtracking,
Mm-hmm.
so if suppose we go into sub problems,
Mm-hmm.
but if we want to come back to that previous state
Yes.
to identify other sub problems, we can say to go
Right.
to other sub problems, then we have to do backtracking, and you can say
Mm.
that backtracking is kind of DFS.
Sure. Yeah.
Yeah.
Okay. Yeah, that makes sense, right? And do you also want to elaborate on when you said, okay, you explore something and then you
Hmm.
backtrack? When you
Hmm.
backtrack, like what is the idea? Why do you have to come back to that state?
Suppose I can say, like, suppose I can give an example, like I can think of is suppose a tree, binary tree.
Mm-hmm.
It has every node has two children, right?
Right.
So if we have to count the suppose the number of nodes,
Mm-hmm.
right, in a binary tree.
Yeah.
So what we can do is we can go left, left, left. Each time we go
Mm-hmm.
left, we count, we increment the count,
Right.
right? And suppose if we go left, 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 but when we go left, then there can be null, right?
Yeah.
So we
Eventually
have
you'll
to
hit
track.
null. Yeah.
Yeah. So we have to track back to the
Mm-hmm.
previous position and then go
Mm-hmm.
right, because there
Mm-hmm.
can be a right node as well.
Right.
So this is
So,
what I can say is backtracking. Simple way.
okay.
Yeah.
Okay, yeah, thank you.
Yeah.
That makes sense. I want to add few things on that, but let's, anyone else have any other points on that, or anyone you want to add, anything you want to add, or
So
um,
uh, I think like when you have multiple options to take
mhm.
and don't know which option to pick until you get to a result,
Right,
then that's also a place where you try and
yeah,
roll. So I say like I have two options here.
right,
So it could be like the other person said, it could be trees, or it could
mm-hmm.
be like if you want to check like if this is going to make the longest palindrome,
Right,
I want to try and see if it makes it good. Otherwise, I want to come back and
yeah.
do
It's
something.
more like you have certain, you come to a point where you realize that okay, this is not uh, giving me a solution, or
Yeah,
there are some constraints, then you have to go back.
yeah.
Uh,
When
yeah,
you have multiple options
right.
and choose without, if you when you randomly choose one option,
Mm-hmm.
then you backtrack it.
Correct. So what you're saying is essentially at any decision point, you have a kind of a range of options, and
Mm.
then you try some, and then you may have to come back.
Yeah.
Sure. Yeah, those are good ideas. Any other points anyone has, or? So I think those were two good notes there. So the high level idea is, if you look at just the raw term, right, backtracking. So you are at a certain path, you are exploring certain stuff, and you might have to get back to a previous state, right? It can be as simple as like the first example that was here about trees. You get to the null node, leaf node, and then you have to come back and explore other nodes. So that's one. The other area, I think the other idea we had here was about, it may not necessarily be, there might be even additional constraints given to you on the problem. And at the outset, you may have options to explore. Um, and actually, you can even apply it on trees, right? When you start on the root node, you on a binary tree, you have two directions to go. So you choose left one, and then you come back and you go to the right. So sure. So both of them captured the same idea, more or less, that you explore some path and then you may have to come back to a previous one. So I had similar points here. Essentially, you have a series of choices, and then you may have to backtrack to some of them. And in terms of uh, identifying a problem, what are the typical characteristics of a backtrack? I think we covered this in the two suggestions you all had. It's about, you have a range of choices. And then in the problems we have today, we'll also see the idea of constraints. So you have constraints where you, based on them, based on those rules, you will identify that I don't need to explore a certain path. It's not a valid state. Or you may explore it, and then when you go further down in your solution, you realize, oh, this is actually not leading me to a globally correct solution. So you may have to come back and try another choice you have. Ultimately, the goal is, the bigger picture is that you are converging towards a goal. It can be like in the two problems we'll see, we have a globally correct solution that we want to arrive at. So that is what you want to lead to. This makes sense to everyone, very high level, but it's good to understand this conceptual idea. And what I'll do is, in the problems I have, the next two problems, I'm trying to follow this kind of three-step approach and to identify where in my algorithm, what is the part where I'm making a choice, where is the part where I'm backtracking and stuff like that. So let's dive into the first problem here, which is an n queens one. So I believe everyone probably is familiar with this, that you have to place n, given an n by n chessboard, you have to place n queens, and the constraint you have is that no two queens should attack each other. And by the term attack, it means that you can't have two queens in the same row, same column, or diagonal, right? So this is in an example 8x8 chessboard, and you are, if you look at this current configuration, you won't see that all of the queens are placed in valid states. Like there are no conflicts basically. So there is no other queen in this column or this row, or even any diagonal. It doesn't conflict with anything. Now there is a possibility that in some configurations, there might be multiple board configurations that will be valid. So this is an example of 4x4 chessboard where you have two valid configurations, right? So it depends on how many solutions you have. But now, so let's, before even digging into the backtracking algorithm, if we are to do it like just brute force, right? What would be the idea? If we are just following a brute force approach,
So probably we'll have a 8 inner for loops, like if it is a 8 by 8 matrix. So like if it is n, I think don't know how we would do that. Oops,
Yeah, essentially what you're saying is you have an 8 by 8 or n by n board. So you're going to like literally have an exhaustive, solution where you try to generate all possible configurations. And
Right.
then for each generate configuration, you check if it's valid or not. If it is, print it. If not, throw it. Right?
Yeah. Yeah.
So, but that would be like, for each square you're trying n possible. So that would be really expensive. So in terms, and that's where like now coming to backtracking and going back to our sort of a template. So if I were to make a choice, right, what are the choices I have in this problem? So if I start with the first row here, topmost, I can place a queen in this cell. I have 9 options basically for placing a queen. Similarly, for the next row, I will have constraints added because I already have a queen here. So I can't place a queen in the same column, for example. So I'll have 8 choices. At a high level, but there will be diagonal constraints. But the point is that as a matter of choice, you have this a certain number of choices for placing a queen, right? And your constraints are coming from the conflicts stuff. And also one of the characteristics of backtracking problem is that uh, your present choice may, like based on your future steps, your present choice can be considered valid or not, right? So for example, if I place a queen in first row, now my next choice, like this column C or this row labeled 7 is not a valid one because of my previous one. And also in recursion, we'll see how we will dig deeper into globally correct solution. But anyways, to simplify this, I think I'm going a little deep into this. But to simplify this, what we have right now is we understand what our choices are. We understand what the constraints are. And the goal is you have to fill this board respecting all the constraints. And when do you backtrack? Essentially, let's say I'm at the last row here, the bottommost. So the backtracking would be the idea that I have checked all the columns, right? And let's say all of them are leading to some conflicts with one of the queens in the previous rows. Then in that case, I have to backtrack to my previous placement of the queen and try another position for that, right? That's the idea of backtracking. So let's look at an example because to make it more concrete. So I have this 4x4 chessboard. So let's walk through a solution space here. So at this point, and let's say I'm traversing row by row, right? And I have the first column, can I place the queen? And I'm working with my first queen. So if I place it here, that's straightforward, right? This is the first queen, no conflicts. What about this? Now I move to the second row, right? So can I place the queen here?
No.
No, right? It will conflict with this column constraint. So similarly, I can't place it here because of the diagonal constraint. So, but this one seems like a valid choice, right? So I go with that. And now I move to the next row. And this can't be, this is not valid because I have a queen in the same column. This is not valid because of diagonal. This is also not valid because of row or column. And this one is not valid because of diagonal, right? So at this point, I have realized that I have exhausted all my potential placements for this row, and there is no valid position I'm left with where I can place a queen. So this is where backtracking comes in. Now you will go back to your previous placement and you will change it to the, and how you got from here to the next one and not this one is taken care by recursion. And we'll see that in the code, how that is working. But Everyone sees this idea about how we identified backtracking here. Any questions?
Uh,
So I changed the position of the queen in I backtrack and change this position and I come back here. So this is again not valid, but this seems valid now, right? And now if you move to your next row, this is a conflict, this is a conflict, this is also a conflict because of the diagonal, right? And this is a conflict, right? So now what you'll do is, again, you back, but this is not even a valid placement, right? You can't even place the queen here because of the diagonal conflict. So this is, you won't even try this. And same here. So now you are actually backtracking to even one further step. So you identified that this position wasn't leading to a solution. This one was a conflict. This one was a conflict. You're done with the possible options here. So at this point, you backtrack here, but you're already at the end of your row. So that means this is also invalid. And that leads to all the way to the first row. So there are 2 points here. One is about when I'm placing a queen, I'm checking the valid placement based on these attack constraint, right? That is not backtracking. The backtracking is more about you exhaust your options for your current placement, queen placement, and you have to backtrack to a previous placement and you have to change that, right? So in this case, I backtrack all the way to the first row. And now I go through this process again. I can't put it here, neither here nor here, but this is good. Yeah. I'm just going through a quick solution. If you have questions, raise your hand. So in the third row, I can put it here. I don't see a conflict. And in the fourth one, this is not possible, neither this, but this looks good. And now at this point, I identify when I switch to the next row, I know that I'm at the end of my grid. So, and that's where I know I have a solution. Right. Any questions on this approach? This looks good.
This is a great explanation.
So this, sorry, there was a lag. So yeah, so let's dive into code mapping, right? We understand this template, we understand the walkthrough. Now, how do we translate this into code? So talking about the choice step, right? I'm trying to place, I'll show you the full code, but I want to show the snippets as well. So let's say you have, okay. So what you have is I have a method place n queens and I was going row by row, right? So when I first call this function, I'll pass row as 0, right? And n is the board, like n by n chessboard. So n is the number, that row count. I have just given this example here, what I mean by solutions. So if you see a possible solution, essentially what this is, every row is a list, right? That is the inner argument. And then this is a list of the lists, right? I have 4 elements. So that's where solution space is. So what I'm doing is I'm identifying my base case. If I'm done with placing all queens, then that's good. That's where I stop. But otherwise, this is where my choice step is. In every row, I have n potential placeholders for putting the queen, right? This is essentially the column index. And then the next thing I do is I start with I0. So I check if that's a valid placement, right? I'm passing the current row, the column that I'm trying to place it on, the board and the n value. If it turns out to be a valid placement, by valid placement, I mean there are no attacks, right? Based on the column, row, and diagonal conflicts. So if there are no conflicts, then I place the queen in the position. Now the next step is using this placement, can I solve rest of the puzzle, right? Does this leads to a globally correct solution? And what I need to do for that is I just need to move to the next row to place the next queen. And this is where like I make the recursive call. And essentially what this is saying is, if you can do that, if you can if this leads to a globally correct solution, then you return true. Then you have solved the puzzle, one configuration. But what if that doesn't happen? Like we saw in our walkthrough example, that sometimes even after reaching the fourth row, you realize, oh, I can't place the queen in any of the columns here. So you have to backtrack and you have to change the position, right? So this is the step that is doing that. So this is saying, if you identify this can't be done, then you backtrack and you basically undo this placement here, where I placed Q in row in column I of the current row. So this is that, and this is essentially the core of backtracking, like the step which is actually taking you back. Yeah. And the last thing is, when I'm done with trying all choices and I realize that it's not leading to any valid state. So that means I can't solve with a given configuration. Does this like kind of modularizing this make sense? And
So dot is the default. And just go ahead. Sorry.
It's okay. Anyone can ask first. Okay. So what I need to ask is like this board row I equals to dot, right? In the backtrack line.
Yeah.
So can we place that line in the if condition, like after return true? If place n queues n row plus one board solution return true. After that, can we put this board row I equals to dot?
So you're saying, I'm thinking.
No, right?
Because if that
no,
is...
so what this is doing is actually, okay, that's a good question. So what this is doing is, this is also taking care of if I can't place the board, if it's not even a valid placement, right?
Okay.
Then I don't even need to go through this.
Yeah. Okay. I got it.
Yeah.
That's like a else condition.
Yeah, it's an else condition actually. And maybe I should write it a little better, because in this code snippet, I'm taking care of two things. It is an else for this, and it is also taking care of.
Oh, that's why. Okay.
Yeah.
Oh, I got little confused, but
yeah. No, but that was a good catch actually.
Yeah.
I think it still work, right? Because initially, the matrices are start with dot. Is it? Initially what the matrix have?
Right, the matrix is empty. In this problem, you have a 4x4. For example, if n is 4, so every cell is empty, and you're just yeah.
Maybe if you initialize with dots, things, right?
Right. Basically, I mean to say, like, there are no placements, so they're all available options. Yeah. So in this case, I'm initializing with a character. Okay, so I can show the complete code if this looks.
One question on the template, Dippy. So
sorry?
Yeah. One question on the template that we are following, the choice, constraint, and backtrack, right? So the last step when we return false, is it the exhaustion of choices or the columns, right? In our case, the choice is the choice we're picking is the rows, right? Where to put.
Choice is the column, right? I'm going row by row, and the choice is like which column am I placing in.
Okay, choice is the column. The first choice is the column.
Right. Like this thing here, for loop is essentially denoting my column. But I think what your question, are you saying that like what case this is referring to?
I was wondering, like, choosing which row to put in or which column to choose, which one of
Yeah.
those is a choice that we
Right.
are.
So the choice is I'm going row by row, which is defined by this parameter in this function. But my choice is defined by the column.
Okay.
So at each row, I have in a 4x4 board, I have 4 choices. Yeah.
Okay.
So
I feel it might be other way, right? Because
It can be other way. I mean, you don't have to go row by row, right? If you go column by column, let's say, if I am trying to place a queen in, first of all, identifying in first column where I can place it, in that case, your choice will be row,
okay,
right? It really depends. I mean, you
right,
can do either way.
right.
Yeah.
I think it's basically returning false for the last, like
Yeah.
previous,
I
the
think
current placement.
once I show the complete code, yeah, you're right.
so just a quick question. I think we touched on that. So we have a if and then what, and then we are assigning dot, right?
Yeah.
So that piece of the code can be written in else as well. Like, can we write if and then else and
Yeah,
then?
yeah. This is actually else only. It's just sort of an implicit thing. But because if it hits here, then if it all goes well, this will never hit this, right? It will just go into recursive call.
Okay, yeah, because the question, sometimes I have faced this issue that where
Yeah.
putting a code in else or if does make a lot of
No,
difference.
it may not be exactly else because after you complete this current choices, you need to go back to your previous board state, right? I think that's the reason.
No, Naga, the thing is, when I'm placing a queen, if when I make this recursive call for the next queen, right? If it leads to a correct solution, then I just return true right here. I'm not backtracking at all.
No, but only if that is true, right?
Correct, correct. So this is in that way it is else. Yes. But
Yeah,
I'm
I mean,
saying
like, are you
that
talking about the inner if or outer if?
no, so yeah, so this else part is taking care of kind of both.
yeah, but I think to Naga's point, I think if we put this in else, right, and if the inner if is not returning true,
Yeah, then it won't
then also
execute,
we
right?
have to, otherwise
Yeah.
if we put else there, then it won't go in that code, like it won't assign dot to it. What I'm trying to say is that if inner if doesn't return true,
So,
right?
it'll always execute this. If you put else, it won't.
Oh, right. Okay, because yeah, that's
Yeah,
that. So that makes sense. So you're saying if this returns false,
yeah,
right now the way I wrote it, it will come here because it's not an else, right? Because
yes,
otherwise it will,
yes,
yeah.
Yes.
Okay, this is one example where you write something and you don't realize.
yeah, because in recursion it makes a lot of difference
Yeah.
having the code in if and else. I think in yesterday's session, also in the afternoon session, we did a similar problem and
Okay.
it was not in the else. So yeah, okay.
Okay, great. I learned something. All right, awesome. So let me show the complete one. You guys can see the Eclipse window, right? I have.
Yes.
Okay. So this is what I was doing. So I start with the solve n queens. This is just board initializing. And I call this function, recursive function, with row 0 because that's where I want to start. And this was the snippet I was showing you. Oh, this is something we didn't cover here. So this is the base case, right? Like when I have exhausted, when I'm done with my all placing all the queens. So we'll look at it in a bit, but let's quickly look at the solution I was showing you. This is exactly the same, right? Yeah. So now what happens when you reach the end? That means you have identified the correct placements for all queens. So in this case, I'm just basically picking the board configurations and I'm creating a string out of it. Since I have to return it in this format, so I'm first creating a list, right? Like a row in that board, and then I'm adding it to my global solutions. that is pretty much that. And then with the valid placement, it is, I'm using these constraints. So here, when I place a queen, passing row, column, and then if this is pretty like, I guess, self-explanatory, that here I'm checking if there is a conflict with any other column on this row on the left side. The reason, so what I'm saying here is if I have, let's say, if I have a queen here, okay. So let's say I have a configuration where I don't have a queen and then I have a queen here. And now I'm trying to place a queen here, right? And I have another position. This is a 4x4 board. So when I'm trying to place this queen, I don't need to check this one because I'm going in sequence sort of, when I'm trying the placements. So in this case, I'm only looking back if there is a conflict. So and similarly here, I'm checking with row conflicts, any of the rows that I have previously explored.
But Dippy, you came from that path only. Do you need to check that at line 17?
Yeah, there's no need to check it.
What do you mean? Like,
because you already came from that path. So you're putting a queen, removing a queen, putting a queen, removing a queen from that row. So seems like line 17 to be doing that.
I think maybe I didn't capture that. So what?
So you mentioned like, oh, can you draw it again?
Yeah. So if I have a board configuration like this, right? And oh, I see what you're saying, because you're not going to do this because you're going to move to the next row.
Yeah. Because this is a current row where you are. So basically,
correct.
This is only one place where the queen would be. Otherwise, it won't be anything. Because when you backtrack, you make a dot, right?
Sure. Makes sense. Because I'm going row by row. Once I place a queen, I move on.
Okay. I have a thought about this. I was wondering if we can pass like a set with the previously placed columns. And then that way the line 21 to 23 can be
I saw that idea somewhere, but I didn't have a chance to check it out. So so do you want to kind of elaborate on that?
Yeah, I mean, it would make the code more complex because then you will have, when you do the backtracking, you will have to clean it. That means add and remove the columns from the set, but it would make at least the line 22 to 24 order of one. I mean, it's just a little optimization. I don't think it matters but just a thought.
For sure. Yeah, I mean, and I think these things have help in the interview, right? When you try about different approaches. This is just like I am also learning by looking at different solutions. So, but it totally makes sense when we are trying to see if something already exists, then set becomes a natural choice. So,
one question. Hello?
Yeah.
So I want to ask, like in this case, we are returning one valid configuration, right?
We are checking if, the current configuration is valid.
We are returning a matrix, right?
Yes.
Of correct valid configuration.
Correct.
So what if we want to return, like you said in the previously that there can be more than one, right?
Right.
So how can we return both whatever valid configuration are? So we want to return all of the valid configurations.
So this is more, I would like to open it to others as well. So I tried with this problem. I got the solution with one possible configuration. Whichever first one I hit, I return that. But I need to adapt my code to kind of
because
go back and try
Yeah, I understand. Because on lead code, it is like we have to return only one, right? It's something like
No,
that.
no, on lead code, actually it returns both. And that's
Both.
why
Oh,
yeah.
oh,
So
I
my
don't know.
solution, like it gives
Okay.
here, so it says, oh,
That's
not
fine.
both.
We can think on that, like, because we are
Yeah,
returning as soon as we get one valid configuration,
correct,
and
correct.
we have to think of, because the interviewer can ask like how, okay, you have written one valid configuration, how,
Yeah,
but it can written one more configuration. Can you think about
correct.
that?
We
So
Yep.
can just call this main place a valid, I mean, solve and queens in a for loop.
Uh-huh. In a for loop for like,
I mean, like you can, uh, what do you call, like, you can put a one, basically one for loop and call solve and queens, and
uh-huh,
recursively call in solve and queens. Basically, you have the first function will use a first row as a initial condition, like you put it in a first row first column, and
right,
then recursively call it.
uh-huh,
If the recursion, like, if, for example, this one
right,
solve and queens, if it is returning true, then that's
uh-huh.
one solution. Then you start with first row second column, then again, call your solve and queens.
Yeah,
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 yeah.
you mean
And the
that
column also as an input, right? Yeah,
Yeah,
in that case, yeah.
yeah, you mean that if we get a valid configuration one time and we return that, we will see where the first in the first row the queen is placed. If
yes.
we can
yeah,
place it another and then call it, yeah, it can be like that, but we have to think where it's optimal or not, because we have to
yeah,
call it
right.
again and
That's what I was thinking, that the
again.
approach that we are discussing, we are going all the way back to first row,
First
which
row, yeah.
might be okay. But I'm thinking, what if, like, I don't have an example ready, but what if our second valid configuration is coming from a change to, let's say, second row or third row, right?
Then
Then
you
we
don't
are,
return. I mean, you don't return here. Like, you just keep continuing until you exhaust all the possibilities, right? Because we are returning once we have a valid queen,
sure.
we are returning, but we do not return it. We just continue with the different combinations. But
Oh,
your,
I see.
yeah,
Okay.
that's all. Your first in the above, like, other than
Uh-huh.
this, like solve and queens, where you are adding the result to the global result, so that will take care
Yeah,
of different combination.
I see, like this one here.
Yeah, we
Yeah,
have to make some little, I guess.
yeah. I think
What?
below, like where you are getting valid placements, you don't need to return true. You can just skip that, I think. Because
Yeah,
when you skip it, it will
you
just
need,
keep continuing until it
yeah,
was all the different combinations. That's the only thing.
recursion. By using
Oh,
recursion,
okay, okay. Here I'm just returning true the moment I find
Yeah, you don't
like a
need to
valid
return.
one. Yeah.
Yeah, you just exhaust all the combinations.
Uh-huh. Okay. Yeah,
And
that
that will take
is,
care of
I
the
can
printing
try.
off.
Yeah, I'll just complete the code after this
Yeah.
session, but yeah, thanks.
I have a question. Like, I was thinking other way of using this valid placement thing. So
Yeah,
instead of we checking for every placement whether that row, column, and
yeah,
diagonal are safe or not.
right.
Instead, if whenever we place a safe queue, we
Uh-huh,
make that whole row, column, and diagonal as true or false, like that.
uh-huh.
Uh, uh, would that be any way optimize the valid placement? Like, so you
So,
got my point, right?
So actually,
uh,
one example I have seen, I mean, a long time ago was I saw this long time ago. So
mhm.
one way is you can actually use two lists. One is like a column list and a row list. You can actually store like, column value and a row value. And while checking, you just check, like, if your current column index exists in a column is just like, order of one. And
Yeah,
also, like,
correct.
in a row list or a column list, you can check. And for the
Mhm.
diagonal, like, I've seen one formula, like
Yeah,
if the
it's like the absolute value something. Is that the
yeah, if
one?
I place j or
Yeah,
I minus j absolute, if it exists in a column or row, that means there's in diagonal there's a queen placed.
yeah. Right, right. Yeah, but I think the other idea that we had previously, somebody was talking about that blocking the row and column. This is more like that column list.
Yeah.
Hello?
Okay. So this way we don't take extra space, right? Like, but
yeah, we'll save on space, and we don't even need to do this cell by cell. You know.
Yeah. So whenever we backtrack, we need to modify that to false and go to the next one, make that row, column, and diagonal as true. Yeah.
Hello.
Oh, can somebody can be? I don't know if I. Yeah. So the point is there are a couple of ways I see that we can optimize this possibly. Valid placement.
I think there can be many ways to optimize, but I think the overall idea of how to solve this recursion, that is what we are trying to cover. But yes, thanks for all the input.
Yep. I think the approach what you have is more intuitive, and there can be improvisation which can be done.
Right.
But we are
one of the things
the backtracking, so that is like a topic.
Correct. Yeah, and one of the things in general I personally find helpful, for example, this function valid placement, ideas about set, right? They come kind of natural. First shot would be, oh, can I use set because I'm checking if something exists or not, or this snippet that I kind of found, while reading stuff online. This was also intuitive. Like if I don't have that formula about, checking diagonal conflicts right in my head, then how do I approach this, right? This, I'll share this code, but this is quite intuitive about how we think about diagonal conflict. So,
could you elaborate on the absolute value?
That I don't have. Yeah, I don't have that formula right away, but if somebody wants to go ahead and talk about it. Yeah, I didn't I know there is that very neat, formula out there where you can check for diagonal conflict, but I used a little different way. But if somebody wants to elaborate on that, then.
Or just talk about the idea.
Yeah. I think it was more about playing with the indexes. Like when you have, let's say, if I go back to this.
Yeah, I did that a long time ago, but I don't have context now. I mean, I have the code in my OneNote, but
Right. No, that's okay. So I think what if we just talk about the high level idea, the idea is about, like, if you have a diagonal, right? This is 0, 0, and this is 1, 1, and similarly there can be other, like this position, right? So if I write like 0. Idea about that formula is more about playing with this, coordinates and trying to, there is a pattern too that helps you identify whether these coordinates form a diagonal.
Yeah. So if you save this 0, 0 in a row list and a column list, if you do like 1 plus 1, you get 2. So you have a diagonal 2 here. If you do 1 minus 1, you have a left side, the left top diagonal, you have a 0. So there is a collision here.
Oh, yeah. Okay. Yeah.
Yeah.
That's like a little clever trick if you have tried that. Okay. Yeah, but that's, the idea. We can, I can share the formula exactly, and okay. So yeah, so that was this problem here. Now, talking about I was thinking about the time complexity assessment. And the way, and I found one article which really explained it well. So I'll use that. So let me use this here. Okay, so how we are going about time complexity here is, if we are going by like trying to explain the complexity rather than saying, oh, it's factorial or exponential. So based on this code, what we are essentially doing is I'm calling this function n queens. How many, like I'm calling it for each row, right? So for n by n just board, I have this call at a very basic like n times. And this is invocations for ace and queens. We'll see how we account for recursion here as well. But at a basic level, we are calling this for n rows. And now within this function call, what we are doing is we are trying every possible column, right? And along with that, we are placing a recursive call with a smaller subproblem. Like you have placed queen 1, now we are trying to place n minus 1 queens. So we'll say here within each you're doing two parts. One is you're doing you're checking the valid placements. And this is worst case, right? What if your valid placement is the last column in the row? So in that case, this would be also order of n. You're trying different. And second step is recursive call. It's a problem. This is about how usually we use like recurrence relations for expressing recursive call complexity. So what this gives us is overall complexity can be looked upon as P of n is equal to order of n square. N square is coming from this part A, like I'm doing this n times, plus I'm for each recursive call, and this part here, the second one, is essentially you're saying this will eventually converge to n times n minus 1. And eventually you'll get to your base case, which will be order of 1. So this is giving you time complexity of n. Does that make sense? Like breaking it down and questions or does this look good? I mean, I like this breakdown in one of the blogs I was reading. But, okay.
So normally, generally all the backtrackings are n factorial, or do we need to calculate every time if we are doing backtracking problems? Or
so this is a good question. So I was thinking of like I have another problem, Sudoku one. So I was thinking around once I found this one, I was having the same question. I think it will also depend on the, let's say, the problem space you have, right? Like in this case, let's think about, I don't think it will always be n factorial, but I'm trying to articulate why that would be the case.
Actually, it will always be, means it will not be good like order of n square. It will always be bad, but we have to calculate for the exact stuff we have to calculate it, I guess. But yeah, it depends on the space and everything. But it will not be good. It will always be bad because we are exploring every case. We are backtracking, so that's why it will not be good.
Yeah.
That's why I'm more pointed. But we have to calculate it, I guess. Because for every problem, it will be kind of different. But yeah, it will be bad.
Yeah.
Would it depend a lot on the constraints? Because if the constraint is very simple, the complexity would be less. But in this case, we have constraints where we are checking.
No, I think constraint checking is essentially this step, right? So you're just checking whether it's valid or not. But the question is more about what is the nature of the problem? Like how many sort of, how much backtracking it may involve, right? I'm thinking around those lines because
but actually Naga, I think he's correct, because there are some set of branches which you won't explore because of these constraints. So it is in the worst case, you won't go to the full factorial explorations because you're avoiding because of some constraints. So, I mean, like in average case, it may be less than the worst case. So we won't be exploring all possible branches full extent, right?
Yeah, always, not all. Yeah.
Yeah, not always, but we have to think about the worst case. So in the worst case, it's
Yeah, we
always
need to give
bad.
worst case only. So
Yeah.
yeah, like, but we can explain this
Yeah,
too.
of course.
I mean, yeah,
That's
these are
cool.
good questions.
So just to add, like, do we apply like a formula for the permutation and combination in general in backtracking, like NCR formula, what we have for permutation and combination, because that yields to n factorial in the worst case.
Yeah. I mean, I haven't thought through in that terms. That might be a possibility, but I haven't explored it. Like, I think what you're saying is it's more like, okay, I have to make out of n choices and choosing one.
Exactly,
Stuff like
exactly. That's what I was trying to. I mean, I'm not
But
sure.
I guess that formula is valid for the brute force approaches mostly when you're talking about NCR, or because you are just brute forcing it, right?
Yeah, like how do you count for backtracking, right? In that?
Backtracking, I think
Yeah.
there is no formula as such, I guess. But
Mhm.
yeah, for the brute force, you can do these type of things, the factorial and combination, to get the time complexity, I guess. I think I don't know. Yeah,
Yeah.
but what he's saying is, but I think is right, I guess.
Yeah, because when I mean, just taking a step back, like there are a list of combination and permutation problem in lead code, right? And if you see their derivation of the complexity in some of the discussion, they do discuss the like this
I
formula
see.
to come up with the solution. I mean, I have just read somewhere, so I'm not.
I mean, if it's there, like if people are deriving using that approach, might be something interesting to check out. But yeah, sure. I mean, if any of you get a chance to read it, or I'll also look at it.
Sure.
Actually, translates to permutation itself. I mean,
I'm sorry?
you have n rows. I mean, in the first row, you can actually place in the n any of the n rows, and if you place
No,
it
but
on
how
the
many? But the question is not about where are you placing in those n rows. The question is how many times you have to call this function, right? So if you have 4 n by n chessboard, even if you start from second row or third row, that is not important. The important is how many times you have to call this function, right? You have 4 queens and 4 by 4 chessboard. No matter which row you start at, you have to call it 4 times at the best. I mean, minimum. You have to call
yeah,
it 4.
I was looking at that part itself.
Okay. Go ahead.
Yeah,
Sorry.
I mean,
No. I mean, if you place it next, I mean, so there are for every row there are n I mean, there are n values possible. I mean, if you keep apart the diagonal one apart, I mean, diagonal check apart. So every row can have n values. But if you place one value at one row, you cannot use it at the other rows. So for the first row, if it is n, for the second row, it will be n minus 1. I mean, I'm keeping the diagonal check apart. So
okay,
n minus 1, n minus 2 till n 1.
I
So
see what you're
it
saying.
comes up to be n factorial itself if you keep
Hmm.
the diagonal check apart.
I see what you're saying. Like you start from a certain position in a row, and then next row you have one less option because
Yeah,
of the conflict thing. So you do n minus 1.
yeah, n minus 2 until 1.
Yeah, but we have to keep apart the diagonal one, right?
Yeah, that's what I said. I mean, if you
Yeah.
diagonal one is a bit tricky.
Yeah, we can think about, I think, backtracking almost like it's gonna be not like good complexity. It will always be like worst only. Just the complexities of different problems are like some factor, like some are n into n factorial, some are n factorial.
Correct.
So it's just a variation, but yeah, it's always gonna be
And true.
I
It's
guess.
always gonna be
In the worst case, yeah.
Sure. And there would be, like, as we are discussing, there are different ways you can analyze. If you have to reason about it, the way, like I explained, is one way. I like this because it gives me a more systematic approach. But at the same time, it also depends on how you are thinking about the problem. So there might be other ways to analyze it. Combinations, that permutation combination, or this, the way you explained just now about n into n minus 1 stuff, that's fine too. Okay, thanks for, I'm taking notes. It's like good action items for me about going back to the code and stuff. So are we good with this problem? Should we move on to the next one? Okay. So now let's look at this Sudoku one. Very similar. And that's why I thought this would be a good candidate, because it's on the similar lines. So you're given a 9 by 9 board, and you have certain rules, right? Anytime you place a number, like a valid configuration of Sudoku will follow this, that each of these digits will occur only once in a row, in a column, and also within a subgrid, right? There are 9 subgrids, so you have to follow these constraints. We talked about the brute force approach in the first example, so that's here. In terms of choices, in n queens, we were given an empty board, right? In this case, the question is, if there is already a number on the board, of course, there's nothing you have to do there. But otherwise, you have 9 options to place in an empty cell. Constraints are same like the rules, current rules, and also it shouldn't conflict with any of the previous placements. And yeah, so this is very similar. Now let's look at similarly how I'm writing the code. So what I did was, first I said if there is a value in the cell, nothing to do. Otherwise, I have to explore 9 options, right? And I start analyzing each of them one by one. So here I start with k equals 1. So I check if it's a valid configuration, place it. Like you can totally, it's almost like an overlap with the previous code. So I place the value, I check if I can solve, if this leads to a globally correct solution. If so, yes, otherwise I backtrack here. I think having explained the previous one, this seems a little redundant, but the point was that a high level approach, how you can break it down. So I can show the code for this one. So for this problem, it was given that you can assume a unique solution. So we won't land into the some other question we had for, showing all the possible configurations. Otherwise, it's pretty. So I solve with this. I start with this Sudoku solver, and this is exactly the code I was showing. I don't know if there is anything that I should explain here more. This is checking about the grid conflict. Now, this is something it might be a little tricky to come up with in an interview, to come up with this kind of formula, but I guess it also depends on the interviewer, how, even if we say that we'll check for this grid conflict or try some options, maybe okay, but row and column conflicts are straightforward. Any questions, anything that you think we should dig deeper into this, or? Okay, hearing nothing.
Quick question. Sorry, quick question. Where are you checking subgrid?
Yeah, so this is here. I just picked up this formula.
Okay, so the means like checking subgrid is for each cell you are checking
each cell, I'm checking the subgrid that it belongs to.
Okay.
Right.
So my question is like, because the grid is specific to the 9 cells, right? So if let's suppose if you are on the like bottom right, is showing right now. So if you are
Yeah.
on 3, then how you are checking that whether it is part of like a
Globally correct solution.
above and row below and the column left and the column right?
Yeah. So for the column and row, I'm using these conditions. Right? So if I'm checking, for example, 3, I'm
Yeah.
checking that I'm not localizing it to subgrid. So subgrid is just one part, right? Which is here. But overall, I'm checking, if I'm checking 3, I'm checking all the, like here, for the row stuff, I'm checking here. If this value occurs in any of the rows in any other subgrid also. Oh, not subgrid, sorry. It shouldn't happen in the same row, right? Let me just actually, yeah. So if I have to check for 3, 3 shouldn't occur in this row, essentially.
Mm-hmm.
That's the idea. So this is taken care of by this condition. Similarly, 3 shouldn't occur in any of this, and that's here. But this part is only, like is there any other constraint you are thinking that I'm missing here?
No. I'm just trying to understand that row and column is like understood, but the grid is like not clear.
So
Like,
grid is actually checking that when I place 3 here, I'm checking that if there is a value 3 already in the placements I have so far. So let's look at this last one. So if I'm at 3 here, right, and I haven't placed 1 yet because I'm going, let's say, row by row here. So I have 2, 8, 4, 6, 3, and these 5, 7, 9 in my grid. So all I need to do is, if I have 3 somewhere else, like what if I already placed 3 here, then it won't be valid. Right? So this is like that clever formula that I found online. So it's about checking, playing with these indexes, which ensure that I don't cross my subgrid.
so other ways, like can we apply, can we find out, because we know it's a 9 cell in total.
Yeah.
So like a loop through and just going through, that could be also possibility, right?
So you're saying that that might be actually better. So you're saying I have row and column value where I'm analyzing, and I can, since it's a given 9 by 9 board, can I just use some simple math to find the
because
bounds?
it's reachable from that particular cell, right? Because so I minus 1 j or I minus 1 j minus 1 I plus 1 j plus 1. So
Oh yeah, correct. This was the similar idea I was using in the last problem. Yeah, that makes sense. Actually, that's more intuitive. We can try that out. So you're saying if I'm at 3, just go 1 row back and 1 column back. That will give me 2, right?
Yeah.
That way I can check it. So
that would be simple, but I think in the interview that would be easier to come up.
Easier to come up with. Yeah, definitely. I mean, honestly, I can't come up with this formula in an interview. This was more like capturing the idea. Yeah.
Even that is tricky, right? So if you are at 2, so you have to know like what the border is for 2.
No, for sure. I mean, we have to additionally also make sure we are having a sense of the boundaries of the subgrid.
Yeah, you
So
should have
yes. But I think the earlier idea somebody was sharing was, rather than thinking about this modulus and complex, evaluation, if we can think more intuitively, like what you said, find out the boundaries, maybe traverse 1 row up, column, and stuff.
Yeah, finding out the boundaries for each and everything is also like that, right?
Yeah, it will also be
yeah.
Compute intensive maybe.
Yeah, that's true.
So now, any other questions on this? Before I wanted to talk about one thing about the complexity stuff.
For each empty cell, you don't check what already exists. You just like try them all value, right? 1, 2, 3, 4, 5,
Yeah,
6,
I'm
7,
trying
9.
like, yeah.
So you don't need to check like what already exists on that row and that column.
Correct. I try all the possible values like in an order starting from 1 to 9, and then, but I only go with exploring it further if there is no conflict. Right? So for example, here, if instead of 4, I start with exploring 1, but I don't go further down that option because I already have a 1 in that row. So I don't evaluate rest of my board with 1 here. I know that that will be inconsistent. Does that answer your question?
So I'm thinking, would it run better if we kind of, you know, keep track of what value, what could be the valid value for this cell?
Oh, you're saying even further narrowing down the set. But I think there would be a trade-off, right? If you do that, essentially you're maintaining some sort of set, right? To kind of say, okay, I have already tried these, don't try that. That may add to the space complexity. Correct? Because all the cost, the cost that we are paying for trying different options, if you think about it, is not that much because we are not going deep into it. We are doing this valid, well, as I'm, it's kind of a trade-off actually. Yeah, because I'm checking this valid placement versus if I maintain a hash set.
Yeah, it's difficult for me to see, but you know, I just my idea, just my thinking, you know, we know that you know, there's some value right there, and then extra space could be very small in this case because the grid is only 9 by 9.
Yeah, true. Actually, that can be a good idea. Yeah, thanks. Yeah. Okay, so that's we identified some optimization there.
So it seems like the main meat of the problem is mainly like, you know, when do you backtrack, like, you know, it's a is valid, like in this case it's a is valid, and in earlier case it was also like similar, like is valid.
Is valid is not the backtracking step. The backtracking step is
yeah, the main backtracking logic is almost same compared to previous and this, but
true.
the main logic is like the is valid method is one which is
is valid, and the recursive one is the present choice leading to a globally correct one. Yeah.
Okay.
Now, the one other thing I had was about coming back to the complexity. So I didn't analyze the complexity of this using the recurrence one because, and we can do that now, but one thing that I noticed was it depends on the number of empty cells. For example, one analysis can be make a very simple case. If I only have one empty cell in the Sudoku, how many options do I have to try out there? It's like 9 options, right? But if I have 2 empty cells, then it can be 9 to the power of 2 because I tried 9 options here, but now I have to, try different options in the second cell. I may have to backtrack. So it's like 9 times, 81 options. So that was also an interesting idea, but so it will lead to, like, if I have x numbers or n numbers of empty cells in this problem, then the complexity will be 9 to the power of n. Yeah, this is something would be interesting to, in general, we know that complexity will be bad for backtracking, but how to go about it is there are different approaches to it. Any questions on that? Yeah, so these are the two references I found. The first one is I followed the first one to come up with the choice and constraint stuff. And there's another link which explains the complexity derivation I was talking about. Yeah, pretty, like, it's almost just an hour. But this is pretty much what I had for today in terms of backtracking. Are there any things you want to discuss on any of what I talked about, or?
Yeah, I really like the template approach that you have chosen, Dippy. I think I'll
Okay,
solve
yeah.
few more with that template approach and try to get
Yeah.
very familiarized with that. Thank you.
Yeah, I think I just want to add there that though the solution is similar, but I think it kind of gives some like visualization on how to approach these kind of problems. So
Yeah.
this is really helpful.
Yeah, like initially when I was picking Sudoku, I was like, it's almost the same as previous, but I thought it will help to see the pattern rather than picking a completely different one. So.
Yeah, these are the two complex backtracking problems. Yeah. So it's very clear to me now. Yeah. Thanks, Dippy.
Okay.
Yeah.
Sure.
So one DP, I had one request that I'm not sure if we have more session or recursion, but going to the point of complexity, as we discussed the n factorial complexity to some extent in these problems, right?
Yeah.
So if we can pick some problems which are of exponential complexity, and can differentiate between between the complexity of factorial versus exponential, that will be really helpful.
Yeah. I think in just this case, just like Sudoku happens to be, I think, like 9 to the power of empty cells, which is different from n factorial. But yeah, to your point about exploring a little, wider net of problems and seeing how they vary. Yeah.
That will be helpful. Thank you.
Yeah. Sure. So I got really a lot of good ideas in this session. So I think I'm going to look into them. But thanks a lot for the feedback. Anything else before we close for today? Okay.
Yeah, it was a good session, Dippy.
Yeah, it was really awesome. Thank you, Dippy.
Thanks.
I'm gonna start the recording.
Thank you.
Sure.
Thank you.
I should give credit to